Okay, so we're going to talk about Einstein's equations and then actually using them.
Okay.
In astronomy and cosmology. So first of all, the stress energy tensor, or the energy momentum tensor, is Tij, and for perfect fluid, which has pressure P and density rho, the energy momentum tensor is P Gij plus rho plus P UIUJ, and UIUJ are the I guess they're called proper velocities of the perfect fluid. Okay, there's a special case in which P is minus rho, and then things become particularly simple. Namely, you get T Ij is just minus rho Gij. And that may seem strange, but it is basically the universe we have now, and the rho is what we call dark energy. Of course, the present universe is more complicated than that. A, it's not a perfect fluid, or we wouldn't be here. And secondly, it's not exactly P plus minus rho. It's rather that the main energy density is dark energy, which is like a perfect fluid, P plus minus rho. And one way of getting this is to have the energy density be just positive potential energy. And so when you expand the box, you get more energy, and that's negative pressure. Whereas normally you expand a box with an actual gas inside, the pressure of the gas expands the box, and so the gas cools off and has less energy. So this is this rho that we're talking about here is equivalent to a cosmological constant 8 pi big G rho, where big G, of course, is Newton's constant. Now, whatever we say about Tij, we want to make sure that it's defined so as to satisfy a conservation law, and the conservation law is T Ij semicolon I is 0. In other words, the covariant divergence of the stress energy tensor vanishes, and that's di Tij plus gamma I Ic. Although if I'm writing this carefully, I would write it Ic like that, Tcj minus Tic mc ji. What we're doing here with the covariant derivative is that we compensate with Christoffel symbols, and for the upper index, where we have this term, and for the lower index we have that term. Okay, so this is then this conservation law, and now Einstein's equations, which we'll sort of derive in a moment, but Einstein's equations are R Ij minus a half Gij R is equal to minus 8 pi big G over c to the fourth Tij. And let's see, I should remind you what these terms are. The Rij itself is Ri Mn, let me make sure I get the right index here. M I K. No, I've got no. I'm screwing it up terribly. Its Ij is. Sorry, I'm using two different, very different notations here. Let's just put an N and an N there, and then okay. So it's the trace of the curvature tensor, and remember the curvature tensor. The easiest way to write that is to say that R I M N K is let's write it as a commutator of the kth derivative plus gamma k with the nth derivative plus gamma n. And the gammas are 4x4 matrices made up of the Christoffel symbols, and there's equation 11, 352 in one version of the notes. I keep updating the notes, and the equations change. So anyway, so there's a curvature tensor. You take the trace once, and you get Rij. You take the trace again, and you get R. And in fact, we could take the trace of this equation, and then, in other words, we would do G Ji, for example, R Ij, and this would give us an R in the front there, and then we have minus a half G. Yeah, let me pull this like that. And then over here we have Gji, Gij, and this would then be a sum of delta Jj, which is just 4, and that's R equals minus 8 pi G over c to the 4th. And then we have Gji, Tij. Well, this would give us R, this would give us minus 2R equals minus 8 pi big G over c to the 4th T. And so this is the equation that the Ricci, I guess it's called the Ricci scalar. Anyway, the scalar curvature is then 8 pi big G c to the 4th T, where T is the trace of the energy momentum tensor. So another form of Einstein's equations are just R Ij is equal to minus 8 pi big G over c to the 4th Tij minus T over 2 Gij. Although one should probably absorb that minus sign because it looks kind of silly that way. If we're in empty space, then empty space without any dark energy or dark matter, we just have Rij equals 0. So an approximate form is Rij approximately 0 in empty space. Well, it's exactly 0 in really empty space. But if we have dark energy, then there's another term due to this, but the other term is essentially, well, the dark energy density is very small compared to the local density of a star or a planet and so forth. Okay. All right, now, I didn't derive any of these actual formulas, but let me show you how one can derive them, which I think is the simplest way of deriving them and the best way of deriving them. Namely, we'll write the Einstein action. Now, what is the Einstein action? It's sometimes called the Einstein-Hilbert action, but I don't think Hilbert deserves any particular credit here. Anyway, the Einstein action is basically the simplest action you can write down, and it's minus c cubed over 16 pi big G, an integral of r, square root of the absolute value of the determinant of the metric tensor with, lower indices, and then d4 of x. Okay, now this part of it is just a real scalar. Okay, and what happens is when you make a coordinate transformation, the volume element transforms as the square root, as 1 over the square root of the determinant, and so the product of the two is invariant. Another way of writing this, of course, is to say that this is minus c cubed over 16 pi g times an integral of g I k r I k square root of g d4 x. Okay.
Not c to the fourth.
Excuse me?
Not c to the fourth.
No, c is it's c cubed. There may have been a typo in the book.
Okay, great. There it is.
It's c cubed. Well, all right. Let me just explain the subtlety here. If you're talking about this as dt, dx, dy, dz, then it would be c to the fourth.
Okay. Yeah.
But
okay.
if you're talking about a dx0, dx1, dx2, dx3, then you've got an extra c here because dx0 is c dt.
Yep.
So that's the subtlety there.
Okay.
Now, the way to get the field equations is to vary Gij, and so the variation of the Einstein action is, well, it turns out that it's quite simple. From here, you see that varying Gij is going to give us an Rik and a square root of g. But then you've got the problem of what happens to Rik if you vary Gik, and what happens to square root of g. And so there's a certain amount of arithmetic that I'm going to skip. It's exercise 1145. And what you find is that this is minus c cubed over 16 pi big G integral Rik just from that term. And then the rest of it is minus a half G Ik R, and then square root of G variation of G upper IK d fourth x. So it's a variation here of upper IK. And so this, of course, gives us the equation that what's in here is 0. And for some reason, that tensor has been conventionally written as GIK, namely RIK minus a half GIK, the scalar equals 0. So this is the field equation that you get if you just use the Einstein action. Now, let me just say a few words about this Einstein action. What you see is you've got to have something integrated d fourth x, but you want d fourth x to be a scalar, so you multiply by square root of g. Then, what's the simplest scalar that you could think of that would have something to do with the curvature of space-time? Well, duh, it's the scalar curvature. And so it's kind of obvious that once you have Einstein's point of view, this has got to be the action. And if you then carefully vary G upper ij, you find that you get the field equation that I wrote down originally. Well, I wrote it down. It's which field equation is it now? It's this field equation for no energy momentum tensor, because of course we didn't put any matter into the action. Okay. So the way we fix that is we put in a conventional action for matter, and the conventional action for matter is defined such that in other words, if you write a field theory with matter, you make sure that you satisfy this equation. The variation of the matter action is equal to minus 1 over 2c, the stress energy tensor, square root of g, the variation of GIK d fourth x. So in other words, you define the stress energy tensor this way, or let us put it this way. This is the conventional way of defining it. If you do define it this way, then what you get is the variation, but by setting the variation of the Einstein action plus the matter action equal to 0, you get that the sum of these two things is 0. That is, of course, what I mean here is you have an arbitrary variation of GIK, so this plus this has to be 0. And so then what you get is the equation we had before, namely RIK minus a half GIK R is equal to minus 8 pi big G over c to the 4th T ij, and I had to write it in a somewhat odd way. Or equivalently, if you take traces, you can somewhat simplify the equation to this form. So these two sets of equations, one for empty space and neglecting dark energy, and the other quite a general equation, namely this equation. These equations follow then from the principle of least action applied to the Einstein action and the conventional matter. Okay, well.
So R is
the
scalar curvature. That's invariant. also?
It's a scalar.
Right, so it's going to be invariant.
So it's invariant in that if you change coordinates, r of x prime equals r of x.
Okay.
Where x prime and x refer to the same physical point.
Yeah.
All right. Okay, now, obviously, these equations are hell on wheels. If we try to use an accurate TIJ, you know, taking account of all the galaxies and stars, it would be totally impossible. We go to the perfect fluid case, it's still completely hopeless. Okay. What we where we can make some progress is by imposing some symmetry. And what are the symmetries? Well, first of all, you can imagine that you're dealing with either a universe that is static or a system that's a subset of the universe that's static. And what you always would impose is isotropy, that is to say, in different directions everything looks the same. And in fact, normally you say it's not only isotropic but homogeneous. Anyway, if we do that, then what we get, and I don't know why I wrote it this way. I think I'm going to have to change notation just a little bit. All right, so I'm going to try on the fly to change notation. So what we'd have then would be ds squared, which is minus the proper time squared, and we'd set this equal to minus. So under these forms, if we're talking static and isotropic, and I'm not sure whether we have homogeneous. No, maybe not, because we might be wanting to do, for example, a Schwarzschild solution. Well, it's hardly homogeneous because it's a point mass at the center. So it's just static and isotropic. Then we would have minus b of r dt squared, and then plus a of r dr squared, and then plus r squared, and you can call this d omega squared if you want, so d theta squared plus sine squared of theta dt squared. Okay. So this is almost always in relativity you have this combination. Okay? That's from isotropy. And it's almost always you choose coordinates so that you have an r squared times that. And then for the case in which we've got just static and isotropic, you've got two functions of r. And this is called standard form. It's chapter 8 of Weinberg's book on gravitation, as opposed to the new book on Weinberg. Anyway, what we see here is that GRR is equal to A of R, G theta theta is just R squared, G phi phi is R squared sine squared theta, and of course G00 is minus B of R. And moreover, the thing is diagonal. obviously the metric is diagonal because ds squared just involves t squared dr squared, not dr dt or dr d theta and so forth. And so once you have this, you can calculate you can calculate Rij and so forth. I don't think there's any point in trying to go through this, but well, although actually I say this isn't a point. I think it would be useful, but I'm not going to do it, at least not in this lecture. But what we could do would be to compute Rij, and then just set Rij equal to 0. And in other words, we'd be neglecting dark energy and solving this in empty space, say around a point mass. And then we could derive Schwarzschild solutions, which is ds squared is equal to minus 1 minus 2mg over c squared r c squared dt squared plus the same thing, 1 minus 2mg over c squared r, but to the minus 1 dr squared, and then plus r squared. Let me just write this as d omega squared. In other words, d theta squared plus sine squared dp squared. So this is the Schwarzschild metric, and this then is the solution of for the space-time metric around a mass m. And there's a singularity here when r is equal to what's called the Schwarzschild radius, r sub s, which is equal to, let me just write it down, it's 2mg over the c squared, because then if r is 2mg over c squared, we get 1 minus 1, which is 0, and 1 over 0 is infinity. This is not a physical singularity. It's an artifact of the coordinates, the choice of coordinates. But on the other hand, it's a significant singularity, as we'll see here in a moment. On the other hand, for the sun, this R Schwarzschild is about 2.95 kilometers, whereas the radius of the sun is equal to about 700,000 kilometers. In other words, 10 to the 5th kilometers. So the Schwarzschild radius is way inside the sun, and so we can use the Schwarzschild solution outside the sun without worrying about these terms without worrying about the first term being 0 and the second term being infinite. And in fact, Einstein used this solution, or his version of it, to predict that the perihelion of Mercury would precess by, I don't know, 21 seconds per century or something. There was, let me just get a drink of water, and I need to give you a candy because you asked me a question. So here's the candy. The precession of the orbit of Mercury was observed in the 19th century, and people also observed that Uranus was, I have to be careful how to pronounce that. Uranus was moving in a way that didn't completely agree with what you'd expect from Jupiter, Saturn, and the rest of the planets, and the Sun, of course. And so the person who noticed that predicted there'd be another planet, and he said where it was, and I forget the guy's name, but he was very good at calculations. And it took somebody with a telescope only a half hour to find Neptune when this guy told them where to look. And so then the same guy who was great with calculations predicted that there was another planet that we couldn't see because it was too close to the Sun, that was screwing around with Mercury's orbit and caused this precession. And people called that Vulcan because it would have to be very hot. And they looked for it, but nobody ever saw it, and then Einstein explained what was happening. Okay, let's look again now at dt. What is dt here? Well, dt is, if we're thinking about a case where there's no movement of dr or d angle, then dt is d tau over the square root of minus g00, and that is then the proper time divided by the square root of 1 minus, well, effectively it's Schwarzschild radius over r. And so what happens here is that from r much bigger than the Schwarzschild, so now I'm going from the Sun to the case where we actually have a black hole. So we have imagined the star is collapsed within its Schwarzschild radius. Then we have empty space in a region outside the collapsed star up to the Schwarzschild radius, and then of course beyond the Schwarzschild radius. Now we can imagine letting the variable r come in from infinity to the Schwarzschild radius, and when r is bigger than the Schwarzschild radius, this is less than 1, but then it gets to be 0. And so what happens to the laboratory time observing this? Well, what you see is that the whatever object, if you, in other words, the clock that you send in toward the black hole, as it gets close to the singularity, the time interval between ticks gets enormous, and that's the slowdown of the clock as it goes into a deeper gravitational field. And once again, go to the movie Interstellar, which you still haven't watched.
No, I haven't watched. There's a lot there.
Yeah, I mean, it's a great movie.
Yes.
Especially for somebody who knows some science. Anyway, that's why the space traveler, when he came back, was so much younger than everybody on Earth. Moreover, what happens is the clock, as it approaches the Schwarzschild radius, it actually stops ticking effectively. In other words, time is frozen. Another way of thinking about it is, suppose you have a photon that's emitted just outside the Schwarzschild radius. Well, it'll have its natural frequency associated with d tau between ticks, or between the maxima of the wave. But when we look at it in the lab, it'll be incredibly redshifted down to 0. And so you can imagine that if the light is actually, if the photon's actually coming from the Schwarzschild radius, be redshifted down to 0, and you wouldn't see anything. So people call these things black holes. I think it was Wheeler who invented the term. Anyway, the point is that, what am I trying to say? So that's why he called them black holes. But in mid-70s, Hawking pointed out that because the gravitational field in the vicinity of the black hole would be so enormous, it could pair-produce particles, and so the black holes wouldn't actually be black. They'd be radiating to some extent. And in fact, radiation is such that the black holes don't last forever, and in fact, they have a lifetime. And the lifetime of the black hole, so this T is not the energy momentum scalar, it's the lifetime of the black hole. And it's a curious number. It's h bar c cubed over 8 pi, Boltzmann's constant, Newton's constant, and then the mass of the black hole. And so this is something wait a minute. I'm sorry, this is the temperature. Yeah, I was just looking at this night. So this is the temperature. And so what you have is that the temperature is pretty low for a really massive black hole. On the other hand, the thing radiates, and the time until the time that the radiation goes on, in other words, until the black hole has radiated away all its energy, is 5120 pi big G squared m cubed over h bar c to the fourth. So this is a really weird combination of constants, as is the temperature formula. H bar, Boltzmann constant, Newton's constant, speed of light. Anyway, the time turns out to be that. I think what I did was I absorbed Boltzmann's constant in there. I should have left it there, actually. Anyway, this is the time, the evaporation time, then, of a black hole. And now you see that for a big black hole, the thing lasts basically forever because it's m cubed. But for a small black hole, a small black hole doesn't last so long because it's because of the m cubed factor. All right, cosmology. Now, the observations tell us that the universe is, by and large, flat. And some of these observations, let me see if I can sketch for you what some of the observations show us. What we can imagine is, suppose we have, let me give you a brief review of the history of the universe. It started about 13.8 billion years ago. Our best theory of the very early universe, the first few instants, we're talking nanoseconds scale, is a period of extraordinarily rapid inflation due to potential energy that was so great that it caused the universe to expand very, very rapidly. And the simplest theory of inflation is that some scalar field just had a random fluctuation. So in other words, you've got a big universe that's empty, perhaps. It doesn't even matter whether it's empty or full. You've got a big universe somewhere with fields and particles, and we don't know anything about it. But at some point in the universe, some scalar field fluctuated, and of course scalar fields are always fluctuating. Most of the time when they fluctuate, they just fluctuate a little bit. Well, this guy fluctuated in some tiny region enough to create an enormous potential energy. And then, as we'll see probably next week, that enormous potential energy caused that region of space to expand. In fact, it's this negative pressure argument. Namely, if the potential energy is very high in a certain region, if you expand that region, you get even more energy. And so the whole thing, and if you put that into Einstein's equations, we'll see that this causes an exponentially rapid expansion. In other words, something called the scale factor expands as e to the something or other times t, and the something or other is big. And so there's a very rapid inflation, and then by that time the scalar field has found its way back to its equilibrium value of 0, or whatever it is. It might not be 0, but whatever the minimum energy value is. And at that point, all that potential energy is released as radiation. And that's the Big Bang. But anyway, this is the theory. It's not settled physics. It's in fact, we have a colloquium on Friday where the guy is going to be talking about what measurements might support or contradict this inflationary picture. It's called inflation. I think I may have mentioned to you that called inflation was invented in the 70s by, in the U.S. by Alan Guth. It was also invented in the Soviet Union by Linday. And there probably were other inventors. There were always many inventors who were neglected by history, and it's only the famous inventors who get credit. Anyhow, it was called inflation because at that time there was a real problem with inflation in the United States. And Paul Volcker raised interest rates to something like 14%. The opposite of what Janet Yellen was doing. She has a quarter of 1%. She had them 0. Anyway, so it's called inflation. Anyway, after inflation, the energy of the potential energy released as radiation, and then you have a very hot period of radiation that lasts about 380,000 years. During this period of radiation, of course, you have fluctuations also in energy. And suppose you had some fluctuation that started out as necessarily as a very small fluctuation during the Big Bang itself, that would have expanded during a period of 380,000 years to a certain size. And the rate of expansion is what people call the speed of sound in the quark-gluon plasma that well, it wasn't a quark, it was a quark-gluon plasma in the very early instant. After that, it's a plasma of protons, neutrons, protons, neutrons. Well, actually, it's after the first 3 minutes, it's basically protons, helium nuclei, and electrons. And neutrinos, we don't care about them. Dark matter, we don't know about that. But the stuff that we do know about was zipping around at speeds too high for atoms to form, and the temperature was too high for atoms to form. But the speed at which things expanded in that hot, dense soup is the speed of light over square root of 3. Turns out.
Okay.
And so we know how big that would be. That would be 380,000 years divided by square root of 3 times c. So we know how big that thing is. And now we look at it through our telescopes. Well, all right, what do we look at? It turns out that if you look at the cosmic microwave background radiation, and you then do that famous plot, which is the absolute value squared of the, well, first of all, you've got this plot, which is sort of the whole universe, and you've got, you know, all these dots that where the fluctuations are in false colors magnified by 100,000. But what I'm saying is, actually now I've forgotten, I lost the train of thought. What you do is you get a plot something like this, which is a plot of the absolute value ALM squared, where ALM is, ALM is basically an integral over the sky of the spherical harmonic complex conjugate times delta t d omega squared. Now, if you imagine, it turns out David Spergel was here giving a colloquium a couple of weeks ago, and he explained to me how to think about this. Namely, you can imagine, of course this is my version of his explanation, which may not be, I didn't write anything down at the time, but it turns out that you can effectively approximate this by imagining just one spot of a certain size, namely that size, and then forgetting about the m because you have the spots circular and uniform. So what you have here is really just AL squared equal to an integral PL with delta t, but this is a constant, d omega squared. And so it's basically just the integral of a Legendre polynomial over cosine theta from cosine theta equals 0, which is looking straight at the center, to cosine theta equal to whatever this distance, whatever this angle would give you. And that gives you this. And the location of this peak tells you how big the spot is. And that spot is consistent with this formula. And so that tells you that the light from there just has been coming straight at us across flat space for 13.8 billion years, because the angle that you get, which is this cosine, you integrate dx from, you integrate cosine theta from 0, cosine theta, when the angle is 0, cosine theta of 0 is 1. So you're integrating cosine theta from 1 to 1 minus epsilon, essentially. And from 1 minus epsilon to 1. And the thing is all consistent with space being flat. And so these CMB calculations have given us information about space. Namely, it's basically flat, and all sorts of stuff. Namely, that the universe became transparent about 380,000 years and so forth. But of course, to get all the numbers quantitatively, you need to do a little bit better than this approximation that I'm talking about. But when you look at this approximation here, this thing here, this distance here is around 1 degree, which is what this would be given flat space and also the expansion of the universe. So there's a factor of z that occurs. So this is z here, which is 1100, because the expansion of the universe from 380,000 years to today is a factor of 1100. All right, so I've been doing this rather. So you should read what's in the book, and that would give you a little more detail. Whereas I've been saying things in a well, extemporaneously for sure. In any event, if you assume that if you assume isotropy and homogeneity of the universe, what you get is, and you choose the right coordinates, which are called co-moving coordinates. This thing is minus c squared dt squared. So this isotropy homogeneity, but we're not assuming that it's static. And of course, since we put in homogeneity, we got nothing like the Schwarzschild solution, which has, you know, where everything, the point or mass of some kind at the center. We have then something called A squared, or if you want, A of T squared, times dr squared over 1 minus kr squared plus r squared, and I'm just going to write this as d omega squared. So this is d theta squared plus sine squared theta d phi squared. And so this is a remarkably simple formula. And you know, once you get a formula like this, then your metric is incredibly simple. It's just minus c squared, or minus 1, because this is really dx0 squared. So it's minus 1. So gij is minus 1, and it's just a squared over 1 minus kr squared, and then a squared sine squared theta. Diagonal like that. So this is the sine squared theta, a squared over 1 minus k squared, and 1 minus kr squared. And the remarkable thing then is that this k, we have, of course, you know, general coordinate variance. We can choose whatever coordinates we like. So by choosing coordinates, choosing the right r coordinates, we can arrange for k to be either 0, plus 1, or minus 1. So if it's 0, it stays 0 no matter what we do. It's going around the coordinates. But if k is positive, we can shrink it to 1 or expand it to 1. If k is minus 1, we can do the same thing. And so this is called the Friedman-Robertson-Walker metric, or the Robertson-Walker metric. Someone Friedman gets left out. I don't know why. I've been talking a lot about embedding spaces. You can, all right, there are 3 cases. Let me just tell you about this. K equals plus 1. This is compact, equivalently closed. K equals 0 is just flat. And K equal minus 1 is non-compact. And open. Okay. And what we know is that all observations suggest that, as far as I know, that the universe is flat, and we don't know whether it's slightly open or slightly closed, but it's certainly mostly flat. If it's flat, then you don't need any embedding space at all. It's just 4-dimensional space-time, and you just have minus 1, a squared of t, a squared of t, a squared of t, sine squared theta. And so you can just solve for a squared. On the other 2 cases, you can embed it in a 5-dimensional embedding space. And the normal way people do that is they use the metric that is the natural metric for the 5-dimensional space, namely the minus 1, that's this minus 1, but 4 plus signs because you're embedding it in 5 space. And so then the universe that we know, if it's closed and compact, in this Robinson-Walker picture, is the surface of a 4-dimensional sphere in 5 space.
So how do you get away from not doing it in 8-dimensional space?
You don't need the 8 dimensions.
Okay, you just don't need it.
Yeah. Now, here is something that I don't know the answer to. And I asked Finley, and he said he wasn't sure. He didn't know either. This conventional way of doing the non-compact one in 5 dimensions is -1, 1, 1, 1, -1, 2 minus signs. And so your question, the answer to your question may be that if you go to 6, 7, or 8 dimensions, you can make this -1 plus, 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 plus. I think. In other words, I don't see why you need that extra minus sign. It is convenient, and in the book I describe why it's convenient. Okay, I think we can quit now, and I owe you another candy.
Sure.
Anyway, if it's still on.
Well, I turned it off.
You turned it off.
On or off? Which would you like?
If it's still on, leave it on.
Okay.
If it's off, leave it off. Relativists, hardcore relativists, have been fascinated by black holes for decades. And the big advance was made by Kerr, who worked out the case, the metric for a spinning black hole.
Okay.
And that's called the Kerr metric. I didn't put it in the book, I probably should have. But anyway, it's obviously important because these, you have angular momentum, just random fluctuation of this. I don't know who this is. Oh my goodness, all right. All right, just give me a second, I'll get back to you in just a second. So I'm teaching at the moment. Yeah, hang up and I'll call you in a second. Bye. So what was it?
Angular momentum and
Yeah,
Kerr's
if black holes form, sometimes, well, if they form from stars, well, the stars are typically rotating because they were collapsing spheres of gas.
Yeah.
So a natural black hole has angular momentum. And moreover, some of these black holes at the centers of galaxies may just be that you get so many stars close enough together that you have a black hole condition. And in fact, you might even be able to see this here because it basically is that if you have any, let's suppose we have any uniform distribution of matter.
Okay.
Well, the mass goes up as the cube of the matter. So that what we have, in other words, is where's Schwarzschild radius? Here. The Schwarzschild radius here, if we have a density rho, it's r cubed g with a 2 over c squared. So if we have a uniform density and expand r enough,
Okay.
you're going to get this to 1, and so that's effectively a Schwarzschild radius, effectively a black hole. So it may be that that's why there are supermassive black holes at the centers of most galaxies. All right, I think this is enough, unless there's another question.